afternoon, everybody. Welcome back to this, the third of our 6 lessons. So far we've learned how to leave Earth, and what we find as we do. Immediately we leave the planet, and then we set off to explore further after last week looking at the solar system. We're going into interstellar space now to have a look at the other stars that we have near us, the galaxy itself. And then, of course, next week we'll be going off, leaving the galaxy and looking at other galaxies and looking at the universe as a whole. So good, exciting stuff. So next part of the journey, we are going to be looking at where our solar system sits, along with a swirling collection of other stars known as the galaxy. So part 3, the galaxies. Now the universe is lumpy. Okay, now what do I mean by the universe is lumpy? Well, on the whole, this is a good thing, okay, because things like protons and neutrons clump together along with electrons, and they give us atoms, and the atoms themselves lump together in turn to give us elements, and those elements to combine to give us molecules, and then the molecules lump together to give us the chemicals that we have for the building blocks of the universe itself, including life, all the life forms in it. So it's a good thing that things lump together. So let's have a look. What happens then is we get atoms already clumped together, those protons and neutrons in the middle, and the electrons whizzing around the outside, and they all clump together to give us elements and molecules, and these molecules get together and they form everything in the entire universe, life on Earth. And life on Earth, as it says on there, is amazing. So one of the most useful things to lump things together is gravity, and it's gravity, remember from the previous lessons, that we had to overcome to leave the Earth, and it's gravity that pulled all that gas and dust and the rocks together to form the sun and the planets of our solar system, which we left behind last week. And as we left the solar system and went onto stellar space, we can look back at it, and we can look back at those wonderful gravitational forces and those planets swirling around the sun. Well, guess what? This week we look at how gravity works out here in interstellar space and how it results in a mass of stars orbiting arguably the greatest gravitational force in the universe, a black hole, to form a galaxy. And there is our galaxy, and you'll see that we are on the outer spiral arm of one of the spiral arms of the galaxy there. So our sun will be one of those tiny little dots there that you can just about see, and then orbiting that is Earth and all the other planets where we started our journey. We're now looking back at that solar system. We're actually still in that galaxy. This is taken from outside of where we are at the moment. We're still in that galaxy. Now, you'll recall that our solar system consists of 8 planets, assorted other bodies, orbiting a pretty average star, the sun, in a system that's held together by gravity. Well, it turns out that our sun itself is in orbit around a black hole, along with somewhere between 200 and 400 billion other similar stars. And each of those stars is its own little solar system, and many of them have planets in orbit around them. Many of these planets are almost certainly capable of sustaining life like Earth. But more on that in part 5 of this series. But for now, we're going to look at the galaxies themselves, starting with a reminder as to what exactly stars are. So you'll remember that a star is basically a giant nuclear reactor, and it converts hydrogen gas into helium in a process called nuclear fusion. And this process is kick-started by the tremendous gravitational forces, the same forces that forged the sun and the solar system itself. And eventually, after billions of years, the hydrogen's going to run out. And at this point, the star will have ended its main sequence stage. Its core collapses. Starts to collapse, and its outer layers swell out. Now, a star the size of our sun or smaller, they swell out and turn red, and they become what are called red giants. Now, a red giant, as you can see, is many, many times larger than it was as a main sequence star. So you remember there were, I don't know, was it 1 million Earths in that sun? Well, You can imagine how many Earths would fit inside a red giant. It's enormous. It's one of the biggest single bodies you can find in the universe. And it's at this stage in a star's life, after the fusion, the hydrogen's used up, all turned to helium. But the fusion process carries on. And now helium and other light elements are fused to form the heavier elements. And then after more time passes, even these light elements run out, and eventually all the fusion's going to stop. There'll be no more radiation being released, and the star will collapse in on itself because the gravitational forces trying to pull everything in while fusion's going on are being counterbalanced, being pushed back by all the energy coming out from fusion. So the sun is sort of like wobbling away there with all those forces pulling and pushing, but they're balanced. So of course, once there's no forces being released due to the energy, no more radiation, then gravity wins that tug of war ultimately, and the star collapses in on itself. And as it collapses in on itself, it heats up and it turns from red into yellow and eventually into white. And it's now much smaller and glowing white, and it's now called a white dwarf. Now, the white dwarf for our sun will probably be about as big as Earth, with all the mass crushed down together and squashed in such a dense way. So it's going to be a much smaller diameter than it was as a sun. Now, stars like our sun, stars that are about the same size, they are gradually going to fade out. They'll gradually become colder and colder and become a black dwarf. Now, this takes so long that there currently aren't any black dwarfs in the universe because the universe isn't old enough for all the stars to have burnt out. The universe is still relatively quite young. So stars much bigger than the sun, of course, they end their lives after the main sequence stage much more dramatically. They actually swell out to become red supergiants. Now, you can see on here that in terms of what it's like from a supergiant to a red giant, Aldebaran is at the bottom there is a red giant, but Betelgeuse and the biggest star there on the right are supergiants. So you can imagine how massive those things are. Our sun compared to that is a tiny little dot. Now, again, they eventually collapse. And in the collapse, all the matter surrounding the star's core compresses the core more and more. And suddenly compression suddenly reverses in a cataclysmic explosion called a supernova. So unlike the red giants that collapse back in and just get hotter and glow and get white, and then eventually lose their energy to become black dwarfs, these collapse in on themselves so much that they actually, all that matter compresses and hits itself in the center, and there's an almighty explosion, this supernova. And supernovae are amazing. There is a photo of a star that's gone supernova, and a supernova can outshine an entire galaxy for several weeks. They light up the night sky. They're visible in the daytime, and if it was near enough and bright enough, it would be like having for a few weeks 2 suns in the sky. Even in the daytime you could see it. Now there's a part of the galaxy called the universe called the Crab Nebula, and it's the remnants of a supernova. It was an explosion that was observed in the 11th century, and that's a picture of the Crab Nebula. It's called the Crab Nebula because it's a nebula. It's full of gases and the remnants of a star that's exploded. And apparently it looks like a crab. I can't see it myself. I guess it's sort of like crabbish shape, but there you go. So it's called the Crab Nebula. Even more recently, in 1987, a star in the southern hemisphere exploded, became the biggest supernova that we've seen for 4 centuries. And astronomers realized that it was Sandalak II, Sandalak II, a star in the Andromeda Galaxy, millions of light years from Earth. That means, as it's millions of light years away, the explosion actually happened millions of years ago, because it's taken light from the explosion to reach Earth. It's taken millions of years to get here. So we're actually looking at an explosion that didn't happen that night. We're looking at something that happened millions of years ago. It's taken that long for the light to get, that's how big the universe is. It's taken millions of years for the light to get from that explosion to Earth so we can see it.
So can I ask something?
Yeah, of course you can. Fire away.
So how do meteorites and asteroids happen?
How do meteorites and asteroids? Well, asteroids, yeah. Asteroids, you remember from last week, are a sort of a band of rocks around the sun, just past Mars. And occasionally, well, that's what an asteroid is. Now, occasionally, those rocks move away and start getting affected by gravity. And those sort of rocks and other rocks that are flying around space get caught up by the Earth's gravitational field so much that they get sucked in, and as they enter the atmosphere, the speed they're going at, the air moving across them causes so much friction, it actually causes the rock that they're made out of to heat up and glow, and eventually effectively burns, but the heat melts the rock, and that's why you see a meteorite that comes across or a meteor across the top of the sky, skimming the Earth's atmosphere. And some of them are so big that although they get really hot, they don't actually get destroyed, and a little bit of the rock eventually hits the Earth's surface. So it's a meteor when it's up in the sky, and if it hits the ground, it's called a meteorite. So it's a lump of space rock. And you can go to museums, science museums, and they'll have these meteorites for you to look at in cases. But
So,
yeah, that's the difference. Yeah.
when is the last time it happened? Like, one came into Earth?
Oh, they're happening all the time. If you go out tonight, possibly, if it's a nice clear night, let me have a look outside. It's a little bit cloudy, but if you look roughly sort of northeast, you can look this up on the internet. If you look up meteor showers, it tells you the best times of year to see them, and you go out there on a good clear night. Preferably if you can get away from a city or a town where there's less light pollution, because obviously with street lamps and everything, it kills you. You look trying to look at the stars and there's a street lamp in the way, or people's houses and parties and things like that. If you can try and get somewhere where there's no light, or look through a tube so that it blocks out all the so if you get a cardboard tube or make one yourself, look up at the sky in that direction, you can see zip sort of light dashing across the top of the sky. So if you actually go and have a look at that any evening, but at the moment there are some meteor showers going on. Go onto the internet, just Google meteor showers, and it will tell you the best time of year, the direction to look at, which constellation to look at. And next week we're going to be looking possibly at constellations and doing a little bit of stargazing stuff. So when you come back next week, if you haven't seen some, we're going to be looking at a little bit about staring up into space and how we can observe some of the more interesting things going on, how you can see the International Space Station go over, that sort of thing. So yeah, fantastic. Good question though. Excellent. Love questions, guys, so don't be shy. Okay, so so that's the Crab Nebula. Now, if a star near the sun exploded, so a star fairly near us in our galaxy, in the Milky Way, it will probably blast the Earth out of its orbit, and we could even see the end of life on Earth if it was that close, because of the shock wave that hits the Earth from that. We would see it a long time before. So if a star was several million light years away, or several 100,000 light years away, we could see it explode tonight, but obviously the shock wave wouldn't come for many, many, many years, hundreds of thousands of years later. So we would look at it and say, right, that's just gone off. So the speed of light has taken this long. So we know that the speed of the shock wave is coming behind that. We would be able to work out when the shock wave would hit Earth. We could get blasted by a massive dose of gamma radiation as well, and all sorts of things that could really interfere with life on Earth. Could be quite terrifying in actual fact. And when a star does go supernova like that, you can imagine how big that area is. If you can imagine that inside here, right at the center, was a red supergiant, which is massive. It's millions of times bigger than the sun. So this stretches out across the universe. So any planets or other stars that are in the way, excuse me, are going to get hit by the radiation and by the light and the energy from that supernova. A supernova explosion is the biggest explosion you can possibly have in the universe, bar the Big Bang at the beginning, and that wasn't even a real explosion. So yeah, incredible amounts of energy. So they're all bad then, are they? Supernova and all this stuff. And well, in actual fact, a supernova is something that we really need. You need a supernova, and I'll explain why. Without supernovae, we couldn't even exist, because if you remember, light elements are formed from fusion in the stars. Remember, hydrogen into helium, and etc. etc. Red giant, we get some of the other. Yeah. So stars such as the sun, they fuse hydrogen into. Put that one on there. They fuse hydrogen into helium, and then so on and so on, and they can create. They fuse the protons and neutrons together and make all of the elements up to and including carbon. Now, when a star becomes a red giant, it's then fusing more and more together. So it fuses the helium and other small nuclei into larger and larger nuclei. Nuclei, for instance, larger than iron, can't be formed by this process because too much energy is needed. There's not enough energy in a red giant to do that. However, let's admit someone come into the waiting room. Hello, welcome aboard. Yeah, so much more energy is needed. So the heavier elements are formed when a massive star collapses and explodes as a supernova, because then the enormous force of the collapse can fuse small nuclei into nuclei bigger than iron. And the explosion then, of course, fuses this stuff together, makes all of these elements right up to iron, bigger than iron, and then the explosion scatter those elements throughout the whole universe. So, or that little part of the universe. And that's where the elements that make up the molecules in you, your body, come from. You are literally made from stardust. We're all truly children of the stars. We come from the stars. The atoms inside us, the hydrogen, the carbon, the oxygen, all of the minerals inside us, the vitamins, our body cells, every single atom that makes us up, this whole planet, this glass, this iPhone, everything was forged in the heart of a dying star, a supernova. We came out of this massive explosion. And furthermore, this happened billions of years ago. So if you think about it, your body, what you are, is made up from atoms that are literally billions of years old. Your body, the atoms, the elements inside you are all billions of years old. They've just been recycled and recycled over the time. Incredible, really.
So now, is that your background?
What's that? My background from the stars?
Yeah, so your background.
Oh, on here?
Oh, the video. Yeah.
Yeah, that's my TARDIS. So much of the matter from the supernovae, so all the known elements, is subject to the forces of our old friend gravity again. And all of these elements that have just been forged in this star are going to start lumping together, and eventually they'll form a new star, a new solar system, and the whole process repeats, and the planets and any life again will be made from these elements. It takes cycles, millions and millions of years, over and over again. So I'm anticipating that some of you are wondering, if you don't ask, you are wondering, what's going to happen to our sun? Good question. Oh, just before we move on, though, that's the periodic table. You can download this one from the internet if you look at it. It tells you where each of the elements in the periodic table were made, where they come from. So things like hydrogen was created, came about, whatever you want to call it, by the Big Bang. So hydrogen's been around since the beginning of the universe. All of the other colors there show you what was formed by a large star when that went red giant and made all those elements. Then you've got the supernovae. You've got stuff that's been formed by cosmic rays, so radiation that changes existing stuff and turns it into something else by interfering with the nuclei of that particular element. Stuff from small stars, and there is stuff right at the bottom there, the very heavy stuff that only exists because scientists have made it in a laboratory somewhere. So there you go. So the future of our sun then. Well, our sun, believe it or not, is about 5 billion years old, and it's probably going to continue shining away for about another 5 billion years. That's a long time. Because it's going to run out of fuel. It's going to run out of hydrogen, and it's going to turn into a red giant, and it will engulf Mercury, the first planet, and possibly, depending on what happens, the other inner planets. It could be that Earth is engulfed at that particular thing. So we could have the situation where the Earth and the inner planets are in an orbit around the sun. The sun goes red giant and basically swallows up Mercury, Venus, Earth, and possibly heating up Mars, and then who knows how big it's going to go. Good news is you've got 5 billion years before that happens. And here we are, there's a nice slide here showing that Mercury starting to be engulfed by the sun, being destroyed as it starts to swell up. And then on the bottom right there, that's the Earth that's now being destroyed by the sun that's given Earth all the energy to make life, to make it possible for life to exist on this planet. The sun that's the source of all our power is ultimately going to destroy the planet as well. But of course the cycle starts again, then it goes, remember, it'll then forge some elements, and then it goes on and on and on as a cycle to the end of time.
But except, like, wouldn't it already be destroyed before it gets engulfed, since it gets too hot?
Yeah, it will do. Yeah, we boil away first. But probably the good news or the bad news, when it does become a red giant, it's almost certain that the human race will long have disappeared, because the Earth could have been destroyed by collision with a giant meteor. Remember those meteorites we talked about? There's one passing fairly soon, passing very near Earth. But every so often, a massive rock comes whizzing very close in astronomical terms to Earth. And it could be that one lands on Earth. And the current theory about why the dinosaurs, you probably know this, why the dinosaurs were wiped out, is because it was hit by a giant meteor. And it caused what they call a nuclear winter. And it destroyed about 60% of species on the planet. So it's been, that could happen. It may have been vaporized, as we said earlier, by a nearby star going supernova. We could be zapped, or we could have destroyed it ourselves through war or pollution. We could have killed ourselves off, or there could be, like there is now, a virus. Imagine if there was a massive virus that was even more deadly and more virulent. The situation we're in now, which is why we're all sitting at home. You're not at school, and I'm not teaching in a school, and imagine if an even worse virus was to come about. So the chances of humans being on Earth in 5 billion years' time are actually quite small. So I don't know if that's a good thing or a bad thing, but I certainly wouldn't want to be around when the sun went red giant and it started boiling away the oceans and melting the planet. But yeah, you're quite right. Even before it destroyed the Earth, it would certainly, even if it didn't get as far as the Earth, it would get big enough to be able to boil the oceans away. I suppose we could by then look at moving to Mars, which is a bit further away, or leaving the planet, in some kind of arc, if you like, a spaceship to keep the human race going. But who knows? We might have spread out across the galaxy by then. We may have populated other planets. So the Earth destroying might just be like us moving house, and our old house gets destroyed to make way for a bypass or something. So you never know. Gosh, that's depressing, isn't it? Mind you, we've got 5 billion years, so we've got plenty of time. So after the supernova, what's going to happen? After a supernova explosion, what's left? Well, let's talk about our sun first. The core gets compressed into a neutron star. Okay, so after the supernova explosion, what's left of our giant star? Well, all the stuff that make up the star will be compressed into a neutron star. Now, what's a neutron star? Well, it's an extremely dense object made up of only neutrons. And the neutrons are crushed together so much, it's so dense that a tablespoonful of stars would weigh, get this, 900 billion kilograms. 1 tablespoon. It would weigh the same amount as Mount Everest. So if you can imagine Mount Everest crushed down and put onto a tablespoon, that's what it is. You couldn't lift it up. You couldn't do it. If you put a lump of it on the Earth's surface, it would just tear through the Earth's surface, probably fly out the other side. In theory. In reality, that wouldn't happen, because the only thing that makes it so dense is because there's so much of it. So if you were to take a little bit of it away, as soon as it left the gravitational field, it would expand. A bit like opening a can of Coca-Cola or Fizzy Pop. As soon as you open it, it releases the pressure, the gas comes out, and it stops being under pressure in there. So it's a bit like that, but with density instead of that sort of thing. So now, if the star is massive enough, if it's got enough stuff in it, then it will become a black hole instead of a neutron star. It collapses in so much more that it actually becomes a black hole. Now, what's a black hole? Well, a black hole is amongst the most mysterious and little understood objects that exist in the universe. Now, a black hole is so dense that it has a gravitational field so strong that nothing can escape from it, not even light or indeed any electromagnetic radiation. Even if you could survive going into one, you couldn't send a message back to tell anyone what it was like, because the radio signal wouldn't get out. It would just be pulled back again. Now, they're useful, though, black holes. Now, it's a black hole that our sun and the hundreds of billions of the other stars in our galaxy are all orbiting. At the center of our galaxy is a black hole. And all these stars are going around like a giant whirlpool in space. Now, galaxies can range in size from a dwarf with as few as 10 million stars, 10 million stars, that's a lot of stars, to a massive giant galaxy with 100 trillion stars. And each star orbits its galaxy's own center of mass, and it's estimated that there are more than 170 billion galaxies in the observable universe. So if you think there are 170 billion galaxies, each with 10 to 400 billion stars in, that tells you how many stars there are in the universe.
What type of galaxies are one?
You must have read my thoughts, because guess what we're going to be looking at next? We're going to be looking at galaxies, and we'll talk about what our galaxy is and some of the galaxies, okay? So, although there are over 170 billion galaxies in the observable universe, there's also something they call a future visibility limit. Because the way the universe is, how big it is, we can't see beyond a sort of a horizon. We don't know what's beyond that, because light has taken so long to get to us, we can only see back in time as long as the universe has been in existence. So we can't see beyond there. So we may never ever know how many galaxies there actually are in the universe. We can only see what we can see. Because, as I say, light emitted by objects outside that limit will never ever reach us. So, what type of galaxies are ours? What they are? Well, there are a number of different types of galaxies. We'll go into what the types are here, but ours is called the Milky Way. Now, you can see the Milky Way if you look south on a very, very clear night with no lights. So you want to be in the countryside, somewhere where there's no light pollution, no moon in the sky, and you'll see a sort of a soft band, as you can see on that image on the left, a soft band of stars, all sort of clustered together. And that's us looking out along the galaxy to all the other stars. So all the stars you can see that are stars, not galaxies, are all in our galaxy called the Milky Way. So that's our one, and it's a whirlpool galaxy like the one on the left there. But there are some other galaxies that you can see: Sombrero Galaxy, the Large Magellanic Clouds, the Whirlpool Galaxy, and the Andromeda Galaxy. You can see those, and when we talk about looking out into the universe next week and astronomy, we'll cover where you can look to see things. And if you've got, you can see an awful lot. If you've got a great sort of like somewhere out in the country or somewhere away from the lights, you can see an awful lot with the naked eye without any. If you've got a good pair of binoculars or a telescope, good pair of binoculars is as good as anything, to be honest, because telescopes tend to focus on a very small area of the sky, whereas binoculars, you can see a wider area. But we'll show you how you can look and how you can spot a planet, stars, galaxies, constellations, all the stuff that you can see, including the Milky Way. So there are tens of thousands of galaxies have been catalogued. Mostly have got funny numbers like MZ73 and things like that. Only a few have been given well-established names like Andromeda, the Milky Way, the Magellanic Clouds, the Whirlpool Galaxy, and the Sombrero Galaxy. Okay, so let's just take a moment to look up what galaxy is. Get the old dictionary out, and it says, galaxy, plural galaxies, astronomy, a large system of stars held together by mutual gravitation and isolated from similar systems by vast regions of space. So it's a load of stars gathered together, all held together by mutual gravitation, the same gravitational field, the black hole at the middle. Now, the word galaxy itself is derived from a Greek word, galaxias, which literally means milky, which is a reference to the Milky Way, because early man looked up that band of stars and they thought it looked like somebody had spilt milk across the sky, so they called it the Milky Way. It's the galaxy you can eat between meals without ruining your appetite. So it's the Milky Way which contains our solar system. Now, galaxies are historically categorized by their apparent shape. Here we go. This is your question. What is ours? There are actually 6. Let's have a look at the different types of galaxy there are. We have got spiral galaxies, which is ours is a spiral galaxy. Actually, ours is a barred spiral rather than a spiral, but it's just a different version of the same thing. So spiral galaxies are disc-shaped. They have dusty curving arms. And as you can see, a barred spiral has sort of a bar across the middle. So we're sort of a barred spiral type galaxy, our particular one. Irregular galaxies, they have an unusual or irregular shape, similarly to peculiar galaxies, but they're peculiar as in their peculiar shape rather than an irregular shape. And we have elliptical galaxies, which are stretched out an ellipse, so they're sort of like elongated slightly. And we have lenticular, which is a galaxy that appears to have sort of lines around them, like gaps in them, that sort of thing. So that's how we would categorize the types of galaxies they are. Now, there's a unit of measurement that astronomers use. It's called a parsec. Now, a parsec is really quite a complicated way of expressing large distances. It's all about measuring a fraction of an angle. So when we look at something, we have an angle of 1 second, which is 1/360,000th of a degree. Okay, so we look at 2 objects, and the distance between us and that object is, if you look at it and you look at, say, something like the sun or an object you know that you can use, and you look at the distance and you say, right, where the distance between that and the object we want to measure appears to be 1 radius of an Earth orbit, so the average distance between the Earth and the Sun, and the angle of 1/360,000th of a degree, then that distance between, using a bit of trigonometry, basically Pythagoras, if you like, or sines and cosines, we can work out the distance between us and that object. And we work it out in parsecs. So when we have exactly 1 second of arc, so 1 second, so 1/3,600 degrees of a circle, and the object to 1 Earth orbit radius apart, then the distance between us and them is 1 parsec. Okay. Now, 1 parsec is 3.09 by 10 to the 16 miles, or 3.26 light years. So 1 parsec is actually 31 trillion kilometers. That's 19 trillion miles. And we need that because the universe is so big. So if we were to measure the universe in kilometers or meters, the numbers would be so ridiculously big that it would make it impossible. So we come up with a unit that effectively reduces those numbers down to manageable amounts. It's a bit like saying we measure the distance between here and America in miles rather than meters or inches. Because if it's a few thousand miles or a few thousand kilometers, or it could be many hundreds and thousands of millimeters, it makes it a large sort of unhelpful number. So for instance, if we were to say the width or the diameter of a galaxy in miles, we'd have to do calculations like using numbers like that, which is a very funny number to say. It's 190 with loads of noughts after it. So if you have 1 parsec that's equivalent to 31 trillion kilometers, then that makes the largest galaxies that distance on the screen. Now, the only way to say that distance is and it really does, to me, it doesn't really mean anything because it's such a big number. It's 190 quadrillion miles. What's a quadrillion mile? It's a distance that you and I are never going to probably travel in our lifetime. It's a long distance. So we just say it's 31 parsecs, or it's 31. Do you see how it makes it a lot easier to work with those numbers? Okay, so just a little word. In literature, galaxy, oh, that's the wrong one. When we talk about a galaxy, if we use the capital G, we're talking about our galaxy. It's the galaxy, and it's the Milky Way. Other galaxies have a lowercase g, just a way of writing it. So if you see galaxy with a capital G, it's not at the start of a sentence, then it's referring specifically to the Milky Way. Okay, and oh, I've got another slide coming up here. Oh, there we go. So most galaxies in the universe are actually dwarf galaxies. Okay, as we can see here, there's two galaxies. There's a dwarf one and a larger galaxy, and they're relatively small compared to the other galaxies. They can be about 1/100th the size of the Milky Way, with only a few billion stars. Now, galaxies. This is a guy called Stephen Finkelstein, or Finkelstein. The most distant and primordial galaxy, so the most earliest galaxy we can see ever discovered, it's got a catchy name. It's called Z8 5296, and that's approximately 13.1 billion light years away. It was discovered in October of 2013 by a team of astronomers from the University of Texas, led by this guy on the screen now, Stephen Finkelstein, University of Texas at Austin. So that's the oldest, the youngest, the furthest galaxy, if you like. That's the earliest one we can see. Now, up until 1920, so 100 years ago, most astronomers believed that all of the stars in the universe were contained inside the Milky Way. They thought that was the universe. The galaxy, the Milky Way, was the universe. Now, there was great debate about that, and lots of observations, particularly by someone called Edwin Hubble. And he proved the Milky Way was, in fact, just one of billions of galaxies in the universe. So there are loads of galaxies. Oops. Loads and loads and loads of galaxies. As I say, the oldest galaxy, HT 140283, is also known as the Methuselah star, and it's at least 13.6 billion years old. Now, we already talked about what happened when the sun goes and what's going to happen to the Earth, etc. Well, I've got some news for you as well. There's something else that could prove a little bit tricky for us on Earth, and that is that the Milky Way, our galaxy, is actually heading towards Andromeda. And it's traveling at a rate of approximately 600 kilometers per second. So in the time it's taken us you could work this out, the time it's taken to do this lesson today, an hour, we would have traveled tens of thousands of kilometers by the time we started on our way towards the Andromeda Galaxy. And we are due to collide with the Andromeda Galaxy in around 3.75 billion years. Now, if you remember, that's actually less time than our sun's got left to do its fusion stuff. So we're probably going to hit the Andromeda Galaxy first anyway. You know, you can imagine when we hit it, if we're one of the leading edge stars here, our galaxy is going to hit Andromeda, join together. There's going to be amazing, massive forces interacting with each other, and heaven knows what's going to happen when they join together, when they hit each other, traveling at that amazing speed of 600 kilometers per second. Two galaxies colliding in space. Now, there's another picture of the Milky Way in the night sky. Now, the galaxy, our galaxy, has a relatively low surface brightness. In other words, what does that mean? It means it's very difficult to see from a brightly lit urban or suburban location, from a city or a town, but very prominent when the moon is below the horizon. So if you go out on a dark night, away from the towns and the lights, you will get to see the Milky Way if you look up in the right direction. Now, to give you an idea of how big it is, if the Milky Way were reduced in diameter to a width of 100 meters, so imagine the Milky Way being shrunk down to 100 meters, that's easily thought of, then a solar system would be about 1 millimeter in width. That's how much bigger it is. So 100 meters, 1 millimeter. That's the difference between our solar system and the galaxy as a whole, the Milky Way. Now, inside the Milky Way, there are at least 100 billion planets and anywhere from 200 to 400 billion stars. Now, surrounding it is a galactic disk or a spheroidal, a sphere-shaped halo of old stars and globular clusters. 90% of them lie within 100,000 light years of the galactic center. So, let's think, how fast are you moving right now? If you paid attention, you'd know that our galaxy is moving at incredible rates towards another galaxy. But let's just think about the Milky Way. I said at the beginning, the Milky Way was going round the center. We're on the outside. And it takes us on the outside about 200 million years to spin once. So that means that when the sun and the earth were previously where they are now, so they've gone round once, dinosaurs would have been walking the planet. It takes that long to go around. And it also means that the sun, the earth, you, me, and we're actually traveling right now at 828,000 kilometers per hour, or 514 miles per hour. So that's the speed we are traveling going around the outside of that galaxy. 514,000 miles an hour, which is incredible. Okay, I said also that it was a lumpy universe when we started, and it is even at galactic level and intergalactic level. So the Milky Way and Andromeda Galaxy, we said, are coming together. They're moving towards each other, but they are part of a binary system of giant spiral galaxies, and they belong to a group of about 50 closely bound galaxies. So even the galaxies themselves are gathered in what they call local groups. So although the galaxy itself is where it is, and we've got Andromeda and we've got other galaxies, there's about 50 together, and then there's another big gap, and there'll be some more galaxies gathered together somewhere else, and so on. So even at that level, the universe is pretty lumpy. It's not evenly spread out. I think the fact that it's a lumpy universe is probably really, really a good thing for us, as we said, because things gather together. It means that, as I said at the beginning, protons and neutrons tend to gather together to make atoms, and atoms get together to make molecules, and molecules get together to make, and so on, right up to almost the universal level, things getting together in lumps and bumps, and it's what makes things happen. If things didn't join together, if protons and neutrons didn't join together with electrons, if atoms didn't come together chemically and make chemical substances, there would be no universe to speak of. It would just be a mass of particles just zipping around all over the place. So lumpy universes are a good thing. Okay, so, there we go. That's a little local group. And we're just by Virgo, for those of you that know your constellations.
Why don't we feel like going fast?
That's very good. There's a fairly simple explanation for that. When you get into a lift and you press up or down, you can feel the lift moving. Yeah, it starts to move up. You feel it. I'm going up. I'm going down. Yeah.
Yeah.
Now, if it's a very long lift in a big tall building, once you've actually stopped accelerating and you're traveling at a steady speed, you can't sense the lift moving. It's only until it stops and you get a little jump. Yeah? It's a bit like when you're on a train and it's going along a straight track, and you can feel yourself going side to side, but you can't feel yourself moving until you look out and you see the trees going past. So the human body can only sense a change in velocity. We can't sense when we're moving. Okay? And we've been born onto this planet Earth, traveling at this speed. It's more complicated than that. You think about it. If you close your eyes for a second and think, right, I'm on the surface of the Earth, halfway between the equator and the North Pole. I'm moving at the moment. The Earth's spinning where we are. On our bit of the Earth, we're traveling at probably something around 800, 850 miles an hour. The Earth is going around the sun. So we're spinning and going around the sun at the same time. The sun's going around the galaxy. So we're doing this. And the galaxy is traveling across space. So it's doing this. So we're moving at a sort of a but we're moving at constant velocity. Now, if the Earth was to suddenly stop spinning, we'd know it because we'd want to carry on. It's a bit like when you're in a car and you know a dog runs out in front, or a child looks like they're going to step out. Your dad, your mum, or whatever puts the brakes on, and you move forward. That's what would happen to us. But while you're traveling, you don't feel that. It's only when you go around a corner that you feel you're moving. It's only when you slow down or speed up. So yeah, we're moving at a really weird sort of distance, going round and round and round and round and all over. But we've been doing it all our lives, and we're not changing our speed. We're not accelerating, so we can't sense it whatsoever. But if you just imagine it, close your eyes and imagine what you're doing at the moment, and you're traveling. And not only that, but the universe itself, we'll talk about this in next week, I think we'll talk about this. The universe itself is actually expanding. The dimensions, if you like, in the universe are getting bigger. And that's happening at near light speeds. So we're moving away from some parts of the universe. We're moving away from them at incredible speeds, hundreds of thousands of meters per second. So yeah, and we can't feel a thing. It's amazing, isn't it? You sit in a chair in a room on a clear day with no wind, and you feel like you're absolutely still, but you're actually moving at thousands of miles an hour, just sitting in a chair. It's incredible, really, isn't it? Yeah, good question. Excellent question. Okay, so let's have a look about this thing. This is this week's what we can do type thing. So again, you can download this from the internet, or if you want to, we can get details. I can get it put on the YouTube channel or something. But you'll need some cotton balls, some polyester fabric batting or whatever. You can use any equipment. Glue. It says White Elmer's glue, PVA. That is in this country. Some string or yarn. That's the American name for a certain type of string. A pencil, some red, blue, gold, and silver glitter. And this is how you do it. You get a 30 centimeter disc. So you want a bit of card that you can fold in half. I mean, to be honest, you can make this any size you want. If you wanted to make a meter wide galaxy model, if you got somewhere to store it, you could do exactly the same. But you want to cut out a circle from that, 2 circles, to make it nice and strong. So let's say you're going to do it 30 centimeters. You'll do that. You'll cut them out, and you'll stick some a cotton ball. One of those little cotton wool balls, that sort of thing, or a couple of those to make the center of the galaxy. So let's have a look at what we're going to do. So we fold that poster board in half, trace a circle, 30 centimeters, or however wide you want to do it. So you cut out the circles, so you get 2 circles. Glue them together so they're nice and strong, with the flat sides touching like a stack of pancakes. Let the glue set for about an hour. In the meanwhile, what you can do is you can get your cotton balls together, and then you're going to build a dome of those cotton balls in the center, so that it looks like the center of the galaxy, like one of those. You can go on the internet or have a look at an image of a galaxy and see if you can make a copy of a particular galaxy. That would be quite cool. So put your dots of glue to the cotton balls, hold them together, secure them to that poster board. The dome should be, at this scale, should be about 8 centimeters across and 4 centimeters high. Turn it over and do the same on the other side. So you've got so if you can see on that bottom right hand side there, you've got a sort of a vested cotton balls glued to the top and bottom, and that's the edge of the galaxy. If you're looking at it edge on, and that's from above. So you can pull out the cotton then, once you've done that, into streams and spiral them around the cotton ball dome. So draw out the cotton and make those arms of the galaxy going on there. Then you can dribble some glue on the arms, sprinkle some glitter, blue and silver on the glue. That represents newly forming stars. Dribble glue all over the poster board and the foam ball. Sprinkle just this glue with gold and red glitter to represent older stars. And you can add your model. You add to it by marking the position of our sun. If you're doing the Milky Way, you can get a little cocktail stick and put it in there, and a little label on the top that says "You are here," or "Home Sweet Home," or your home address. You can put your address on there. Mark the sun 8 centimeters from the center inside one of the spiral arms, so 8 centimeters out. You can decorate both sides of your galaxy model. Wait for it to dry, and then you can punch a hole in it, put your string through it, hang it from the ceiling, and there you go. You've got a nice model of the galaxy to go with your model that you built last week of the solar system. So your bedroom is now looking like some kind of astronomical museum. A couple of things. Milky Way is a huge galaxy. Okay, so if you're going to do a 30 centimeter model, each centimeter of that model represents about 3,300 light years. The sun is about 27,000 light years from the center of the Milky Way. That means that if you were to fire a beam of light from the center of the galaxy towards our sun, it would take 27,000 years to get to us. That's how far away it is. So when you get your model, that would be about halfway out from the center. Now, most of the stars you can see in the night sky are within 1 centimeter of the sun, your model. So if you are looking at your model and you were to draw a line 1 centimeter away from where you've marked where the Earth is, those are where most of the stars that you can see are. You think about it, when you look up on a clear night how many stars you can see, pretty much most of those are just one tiny fraction of the Milky Way of the galaxy. So our solar system on that model scale is too small to see. So if your solar system were the size of, it says a quarter, if our solar system were the size of a 10p, then the galaxy would be the size of the United States of America. So if you think, right, this is a model of my galaxy, it's a 10p. If I was going to build a model around that to the same scale of the galaxy, I would have to make my model of the galaxy the same size as the whole of the United States of America. That's the difference in size. Can you imagine if you'd lost a 10p piece in America somewhere and you had to look for it? That's the difference. That's the size of the galaxy to the size of our solar system, let alone the sun or the Earth or England or your village or town or your house or your bedroom or your iPad or your PlayStation or whatever it is in your bedroom. Imagine the scale in that. And this is just one galaxy. Remember, there are 170 billion other galaxies out there spread across the universe. That's how big it is. And we're going to find out about them, how big the universe is and things like that next week. Okay, so some of the materials represent major characteristics of our galaxy. So the central bulge, the cotton ball dome, that's the rounded structure in the center. 6,400 light years of the galaxy center is what astronomers call the bulge of our galaxy. So that cotton ball is 6,400 light years from the center, and that's, if you look at the photos of the galaxies, that's what that bulge is in the middle, all going around that black hole. The disk, that's the disk of stars in our galaxy. That contains gas, dust, stars. It's flat like the brim of a wide hat, and astronomers estimate the galaxy's disk is about 100,000 light years in diameter. 100,000 light years from side to side. The stars, the glitter, the hottest and the brightest stars are blue and white, but these stars live very short lives, only 10 million to a few 100 million years. They spend their whole lives close to where they were born in the spiral arms. Older stars found in the bulge and disk may be yellow like the sun or red. Okay, so you can use your model while you stargaze. So when we look at the stars, when we go out, we're going to talk about that next week, in the coming weeks. You can use that model to help you understand our place in the galaxy. So when you look towards the stars in the constellation, say of Sagittarius, you're looking towards the center of our galaxy. So if you line up your model so that its center lines up with Sagittarius, then align the disk of your model with the Milky Way in the sky, you can imagine where we are inside that galaxy, inside our galaxy. Incredible, amazing. There's a great site if you want to go to. It's www.galaxymakers.org, and you can create a universe. You can make a random universe. You can make a random galaxy. It only takes a few seconds. You give it some information, and it will create you your own unique galaxy or your own unique universe. And again, you can go to places like the NASA website. There are loads of resources out there. And when we do the stargazing part next week, I will tell you where you can look at an observatory, and you can do your own stargazing using a really amazing, one of the telescopes that you can use, radio telescopes and optical telescopes that you can use, and you can ask to get images of parts of the sky that you particularly want. There's so much resource out there in terms of space, the universe and everything. So yeah, next week then, so the space between galaxies, which is where we're going next, is intergalactic space. That's where we're going to go to next week. So we're going to be looking at the galaxies as a whole again, the universe itself, talking about stargazing, looking at that sort of thing. So that's what we've got to look forward to next week. That'll be number 4. So we're almost there. Just got 3 more to go. So I hope to see you again next week to look at intergalactic space. I hope we've had some questions as we go along, which is absolutely brilliant. That's the best time to ask them. You can ask me questions between lessons if you go to my YouTube channel, Physics Demystified. If you can't find me, I'm out there somewhere. You should be able to find me. And so thank you again for joining me this week. It has been absolutely amazing. As you can tell, I love the universe and space and all that sort of thing. So as I say, intergalactic next week. Then we're going to talk about life in the universe. And then the final week, we're going to talk about the nature of time itself. So thank you tremendously, guys. It's been fun. I hope you've enjoyed it. Tune in next week at the same time and find out more on our amazing journey across the universe. And I'll see you next time. Bye for now.